NEC Section 700.9 states that the emergency transfer switch, or ETS, should connect directly back to the parallel link gear. This ensures that emergency loads aren't interrupted or delayed by the parallel link gear or other system components. Regarding the ground fault protection, or GFP, of the feeder, the NEC doesn't specifically address it for emergency feeders. However, since the feeder is not required to have GFP, providing it would not violate the code. If GFP is provided on the feeder, the indication requirement of NEC Section 700.26 and 700.7 can be met by installing a GFP indicator on the distribution board in each building. This provides visual indication of a ground fault on the feeder, allowing for prompt identification and correction of issues. In conclusion, the proposed system can remain as proposed with two modifications. Firstly, connect the emergency transfer switch directly back to the parallel link gear. Secondly, provide GFP protection on the feeder if desired, and install a GFP indicator on the distribution board in each building to meet the indication requirement. Now let's delve into the specifics of each of these aspects. Starting with the emergency transfer switch connection, the primary reason for direct connection to the parallel link gear is reliability. In emergency situations, the goal is to provide power to critical loads as quickly and reliably as possible. By connecting the ETS directly to the parallel link gear, you bypass any potential points of failure or delay that might exist in other parts of the system. Consider a scenario where the ETS is connected to a distribution board that also feeds other non-emergency loads. If a fault occurs on one of those non-emergency circuits, it could potentially trip a breaker and interrupt power to the ETS, even if the emergency generator is running and the parallel link gear is functioning correctly. By connecting the ETS directly to the parallel link gear, you isolate it from these potential disruptions. Furthermore, a direct connection simplifies the emergency power system and makes it easier to troubleshoot. There are fewer components to check if there is a problem, and the path of power from the generator to the emergency loads is clear and direct. Now let's consider the ground fault protection, or GFP, of the feeder. As mentioned earlier, the NEC doesn't specifically require GFP on emergency feeders. However, it also doesn't prohibit it. The decision of whether or not to provide GFP on the feeder is ultimately up to the designer and depends on the specific needs of the installation. If GFP is provided, it's important to understand how it works and how it can affect the operation of the emergency power system. GFP is designed to detect ground faults, which are unintentional connections between a phase conductor and ground. These faults can be dangerous because they can cause electrical shock and fire. When a ground fault is detected, the GFP system trips the breaker to interrupt the flow of current and prevent further damage. However, it's important to note that GFP is not designed to protect against all types of faults. It's primarily intended to protect against low-level ground faults that might not be detected by standard overcurrent protection devices. If a high-level ground fault occurs, such as a direct short to ground, it will typically trip the standard overcurrent protection devices before the GFP system has a chance to react. Therefore, it's important to ensure that the emergency feeder is properly protected by both GFP and standard overcurrent protection devices. Now let's discuss the indication requirement of NEC Sections 700.26 and 700.7. These sections require that there be a visual indication of a ground fault in the emergency feeder. This is to ensure that building personnel are aware of any ground faults and can take prompt action to correct them. The most common way to meet this requirement is to install a GFP indicator on the distribution board in each building. This indicator typically consists of a light or alarm that is activated when a ground fault is detected. The indicator should be located in a conspicuous location where it can be easily seen by building personnel. In addition to the visual indication, it's also important to provide a means of testing the GFP system. This can be done by installing a test button on the GFP relay or by using a portable test device. The test should be performed periodically to ensure that the GFP system is functioning correctly. Now, let's further discuss the implications of providing GFP in the emergency feeder. One potential concern is that GFP can sometimes nuisance trip, especially in systems with long feeders or multiple ground sources. A nuisance trip occurs when the GFP system trips a breaker even though there is no actual ground fault. This can be caused by a variety of factors such as capacitive coupling, harmonic currents, or transient voltages. If nuisance tripping is a concern, there are several steps that can be taken to mitigate it. Firstly, ensure that the GFP system is properly coordinated with other overcurrent protection devices. This means setting the GFP pickup and time delay settings so that it only trips for actual ground faults and not for normal system disturbances. Secondly, consider using a more sophisticated GFP system that is less susceptible to nuisance tripping. There are a variety of advanced GFP systems available that use filtering techniques to distinguish between actual ground faults and nuisance signals. Thirdly, minimize the number of ground sources in the system. This can be done by using isolated ground systems or by carefully grounding all equipment. Another potential concern with GFP is that it can sometimes mask other types of faults. For example, if there is a high resistance ground fault, the GFP system might trip a breaker, but it might not be immediately obvious that there is a fault. This can make it difficult to troubleshoot the system and can potentially lead to further damage. To address this concern, it's important to have a thorough understanding of how the GFP system works and how it interacts with other protection devices. It's also important to have a good troubleshooting plan in place so that any faults can be quickly identified and corrected. In summary, the decision of whether or not to provide GFP on the emergency feeder is a complex one that depends on a variety of factors. There are both advantages and disadvantages to providing GFP, and it's important to carefully weigh these factors before making a decision. If GFP is provided, it's important to ensure that the system is properly coordinated, tested, and maintained. Now let's think about practical considerations when implementing these recommendations. Firstly, ensure that all connections are made in accordance with the manufacturer's instructions and relevant electrical codes. This includes using the correct wire size, torquing connections to the proper specifications, and providing adequate support for all cables and equipment. Secondly, label all equipment and conductors clearly and accurately. This will make it easier to troubleshoot the system and will help to prevent mistakes during maintenance and repair. Thirdly, provide adequate training to building personnel on the operation and maintenance of the emergency power system. This training should include information on how to start and stop the generator, how to monitor the system for faults, and how to perform basic troubleshooting. Fourthly, develop a comprehensive maintenance plan for the emergency power system. This plan should include regular inspections, testing, and maintenance of all equipment. The maintenance plan should be based on the manufacturer's recommendations and relevant industry standards. Fifthly, keep accurate records of all maintenance and repairs. These records should include the date of the work, the name of the person who performed the work, and a description of the work that was done. These records will be helpful for tracking the performance of the system and for identifying any potential problems. Sixthly, ensure that the emergency power system is properly integrated with other building systems such as fire alarm systems and security systems. This integration will help to ensure that the building is protected in the event of a power outage. Seventhly, consider using a remote monitoring system to monitor the performance of the emergency power system. This system can provide real-time data on the status of the generator, the transfer switches, and other critical equipment. The remote monitoring system can also send alerts if there are any problems with the system. Eighthly, consult with a qualified electrical engineer or contractor to ensure that the emergency power system is properly designed, installed, and maintained. These professionals have the expertise and experience to ensure that the system meets all applicable codes and standards and that it will perform reliably in the event of an emergency. Ninthly, remember to keep the emergency power system isolated from the normal power system. This means that the two systems should not be interconnected in any way. The only time the two systems should be connected is when the emergency generator is providing power to the emergency loads. Tenthly, have a plan in place for dealing with extended power outages. This plan should include information on how to obtain fuel for the generator, how to provide food and water for building occupants, and how to communicate with emergency responders. By following these practical considerations, you can help to ensure that the emergency power system is properly designed, installed, maintained, and operated. This will help to protect the building and its occupants in the event of a power outage. Let's now look into NEC requirements for emergency systems and optional standby systems, and their distinctions. Emergency systems are those systems legally required and classed as emergency by authorities having jurisdiction. These systems are intended to automatically supply illumination, power, or both to designated areas and equipment in the event of failure of the normal supply. Optional standby systems are intended to protect private business or property where life safety does not depend on the performance of the system. Optional standby systems are intended to supply on-site generated power to selected loads either automatically or manually. These systems are intended to supply power to public or private facilities or property where life safety does not depend on the performance of the system. These systems are permitted to supply power for any load. Emergency systems are essential for safety, while optional standby systems are for convenience or business continuity. The code requirements for emergency systems are more stringent than those for optional standby systems because of the critical nature of the loads they serve. In this scenario, the emergency transfer switch is connected to emergency loads, and the optional standby transfer switches are connected to optional standby loads. The emergency transfer switch must be connected directly back to the power link gear to ensure that emergency loads are not subject to any interruption or delay. This requirement is in place because the emergency loads are critical for life safety, and they must be supplied with power as quickly and reliably as possible in the event of a power outage. The optional standby transfer switches do not have the same requirement because the optional standby loads are not critical for life safety. These loads can be interrupted or delayed without posing a significant risk to people. The ground fault protection requirements for emergency systems and optional standby systems are also different. Emergency systems are not required to have ground fault protection, but optional standby systems are required to have ground fault protection. This difference is because emergency systems are typically designed to be as simple and reliable as possible. The addition of ground fault protection can add complexity and potentially reduce the reliability of the system. Optional standby systems, on the other hand, are typically designed to protect equipment and prevent damage. Ground fault protection can help to prevent damage to equipment in the event of a ground fault. In the scenario, the feeder is not required to have ground fault protection because it is supplying power to an emergency system. However, the code does not prohibit the installation of ground fault protection on the feeder. If ground fault protection is installed, it must be indicated on the distribution board in each building. This indication is to let personnel know of ground faults so they can correct the issues. Let's discuss the coordination of overcurrent protective devices. Proper coordination is important to ensure selective tripping. This prevents a widespread outage and isolates the fault. Coordination studies determine the appropriate settings for breakers and fuses. Time current curves are used to visualize the tripping characteristics. Coordination minimizes downtime and enhances system reliability. In closing, the proposed system can remain as proposed with the modifications to connect the emergency transfer switch directly back to the power link gear, and if desired, provide GFP protection on the feeder with a GFP indicator on the distribution board in each building. This ensures compliance with NEC requirements and maintains the reliability of the emergency power system.